Welcome to KIN 362 Biomechanics. While this course is a program requirement for many, if not all of you, I hope that you'll glean some new and very valuable information in which you'll be able to put to work later within your profession. So Chapter 0 is truly an introduction to the idea of biomechanics and where we see the use of biomechanics research being used in the field. And so the objectives for Chapter 0 are to define biomechanics, define sport and exercise biomechanics, identify the goals of sport and exercise biomechanics, describe the methods used to achieve the goals of sport and exercise biomechanics, be somewhat familiar with the history and development of sport and exercise biomechanics, define biomechanics, outline the organization of mechanics, define length and the units of measurement for length, define time and the units of measurement for time, define mass and the units of measurement for mass. Many of you are probably planning a career as a physical education teacher or coach or some other physical activity specialist, and you probably are or have been active as a participant in one or more sports or fitness activities. Traditional teaching and coaching methods tell you what techniques to teach or coach, whereas biomechanics tells you why those techniques are best to teach or coach. A good knowledge of biomechanics will enable you to really evaluate the techniques used in unfamiliar sport skills, as well as to better evaluate new techniques in sports familiar to you. So what is biomechanics? There are a plethora of definitions of biomechanics available. However, for this course, we are going to use the following definition. Biomechanics is the study of forces and their effects on living systems. To take this a step further for a more practical application, sport and exercise biomechanics is the study of forces and their effects on humans in exercise and sport. The ultimate goal of sport and exercise biomechanics is performance improvement in exercise and sport. So a secondary goal is injury prevention and rehabilitation. As stated within the text, an uninjured athlete will perform better than an injured one. As many of you probably already knew or assumed this, it is easy to make the connection between why performance improvement is so closely related to injury prevention. However, often there are cases where athletes are injured or not functioning as they should, and they are completely unaware of it. There are four main tactics biomechanists use for improving technique or improving performance: technique improvement, equipment improvement, training improvement, and injury prevention and rehabilitation. Let's take a closer look at what each of these entails and how they have evolved over the years. The most common method for improving performance in many sports is to improve an athlete's technique. The application of biomechanics to improve performance may occur in one or two ways. First, the teachers and coaches may use their knowledge of mechanics to correct actions of a student or an athlete in order to improve the execution of a skill. Or two, a biomechanics researcher may discover a new and more effective technique for performing a sport skill. In the first instance, teachers and coaches use qualitative biomechanical analysis methods in their everyday teaching and coaching to effect changes in technique. In the second instance, a biomechanics researcher uses quantitative biomechanical analysis methods to discover new techniques, which then must be communicated to the teachers and the coaches who will implement them. So how do teachers and coaches become aware of these new discoveries? In order for these professionals to be up to date and effective in their methods, they must be involved in attending conferences and workshops, reading primary and relevant research, and networking with other teachers and coaches. Despite the belief that new and revolutionary techniques are regularly developed by biomechanists, such developments are very rare. The much more common outcome of biomechanics is the discovery of small refinement in technique. One example of technique refinement discovered was by Brown and Councilman in the 1970s. Their research indicated that the lift forces acting on the hand as it moved through the water were much more important in propelling a swimmer through the water than previously thought. This research indicated that rather than pulling the hand through the water in a straight line backward to produce a propulsive drag force, the swimmer should move the hand back and forth in a sweeping action as it is pulled backward to produce propulsive force, lift forces, as well as propulsive drag forces. In 1956, Felix Erasquin, a retired discus thrower from the Basque region of Spain, experimented with an unconventional way of throwing the javelin. Erasquin had experience in barra pesca and a traditional Basque sport that involved throwing an iron bar called a palanca. Barra pesca involved a turning technique, thus Erasquin chose to spin around in his run-up and slung the javelin from his right hand. Several new records were set with this new technique. However, officials at the International Amateur Athletic Federation, the governing body for track and field, became so alarmed that they altered the rules for this event, and this unconventional method was deemed illegal. Moving back, a final example of this technique changing that has taken place is in the track and field event, the high jump. In 1968, most world-class high jumpers used the straddle technique. But at the Olympics in Mexico City, the gold medalists in the high jump used a technique known as the Fosbury flop, which was used by an American from OSU, Dick Fosbury. This included a back layout technique, which was easy to learn and teach. Another area in which biomechanists play a role in improving sports performance is in equipment development. Shoes and apparel constitute the equipment used in almost every sport. The equipment worn may have an effect on the performance either directly or through injury prevention. That said, can you think of any sports in which improvements in apparel or shoes have changed performances? Let's take a look. The swimming suit has changed a lot, and we see how the swimming suit design has definitely changed performance over the years. 100 years ago, swimmers competed in woolen swimsuits and women's suits had skirts. Over the years, wool was replaced by silk and then by synthetic fibers. Essentially, the suits became slicker and more hydrodynamic. Perhaps the most impactful change in suits came in 2008 when Speedo introduced the LZR Laser Racer swimsuit. It was designed by scientists and engineers to minimize muscle vibration and reduce drag with compression panels that streamline the shape of the swimmer. Within 6 weeks of its introduction, 13 world records were set at the Beijing Olympic Games. Swimmers wearing the Speedo suit set 23 world records and won more than 90% of all the gold medals in swimming. Another example includes a change in the shape of the javelin. In 1953, Frank Held worked with his brother Dick, who had some engineering expertise, to design and build a more aerodynamic javelin. By increasing the surface area, the javelin had more lift, causing it to fly farther. Frank Held used this newly improved javelin to break the existing world record for the javelin throw. In 1955, the IAAF implemented rules that limited the size of the javelin so that further increases in its surface area and lift were constrained. Biomechanics has the potential to lead to modifications in training and thus improvements in performance. This application of biomechanics can occur in several ways. An analysis of the technique deficiencies of an athlete can assist the coach or teacher in identifying the type of training the athlete requires to improve. The athlete may be limited by strength or endurance of certain muscle groups, by speed of movement, or by a specific aspect of his technique. One example of a common technique deficiency among beginning pole vaulters involves the athlete's movement on the pole. Oftentimes, the vaulter does not get the hips above the head or hands during the later stages of the vault. This prevents the vaulter from achieving an inverted position, and the heights the vaulter clears are modest. Even though it is somewhat easy for coaches to identify this error and provide the athlete with instructions on how to correct it, many young vaulters do not have the shoulder extensor strength required to swing upside down into an inverted position. Essentially, In order for this vaulter's technique to improve, he or she would need to increase shoulder extensor strength. Gymnastics provides an example of how biomechanics may aid in reducing injury. Typically, judges award higher points to gymnasts who stick their landings, but such landings may involve greater or more dangerous impact forces. These impact forces are the cause of overuse injuries in many gymnasts. A landing in which the gymnast flexes at the knees, hips, and ankles may reduce the impact forces, but it also results in a lower score. One outcome of past research included a rule allowing for landing strategies that reduce these impact forces without penalty to the gymnast's score. An example of biomechanics affecting the design of sport equipment to reduce injury involves the running shoe industry. Following Frank Shorter's marathon gold medal in the '72 Olympics, the U.S. experienced a running boom. Unfortunately, this boom in participation was accompanied by a boom in running-related injuries. Thus, a boom in biomechanics research on running and running shoes began in the '70s. If you've never read it before, I really recommend reading the book Born to Run by Christopher McDougall. This book really is an in-depth look at the history of running, how it's evolved, much of it which has to do with the impact of the shoe industry. Some of the shoe companies hired biomechanists as consultants and or funded research in university laboratories. Of particular note, in 1980, Nike established the Nike Sport Research Laboratory. Christopher McDougall has a few different things to say about Nike's impact on the running world. It seemed that either shoes were too stiff or too soft, both of which led to various injuries such as shin splints, stress fractures, and joint issues. These discoveries led to the modern-day shoes we see now, which intend to provide both stability and cushioning. The word biomechanics really didn't become known until the 1960s, even though research in the field was being conducted early in the 20th century. Some of the earliest examples of biomechanics research include determining the speed at which a baseball was pitched by Walter Johnson in 1912, and mechanics and energetics of sprinting by Archibald Hill in the 1920s. Since, research in sport and exercise biomechanics has increased steadily. One reason for this boom has been the advent of the modern digital computer, which allows for easier data collection and analysis from the high-speed film or video cameras and electronic force measuring platforms. Within our definition of biomechanics, we briefly define mechanics as the analysis of forces and their effects. A more complete definition may be that mechanics is the science concerned with the effects of forces acting on objects. The objects we are concerned with in sport and exercise biomechanics are humans and the implements they may be manipulating in sport and exercise. Mechanics can then be divided into several branches: rigid body mechanics, deformable body mechanics, fluid mechanics, relativistic mechanics, and quantum mechanics. In rigid body mechanics, objects are assumed to be perfectly rigid. In deformable body mechanics, the deformation of objects is considered, for instance, a ball. Any deformations can complicate the analyses. Fluid mechanics is concerned with the mechanics of liquids and gases. Relativistic mechanics is concerned with Einstein's theory of relativity. So every time you measure an object's velocity or its momentum or how it experiences time, it's always in relation to something else, like the speed of light. And quantum mechanics is concerned with quantum theory. Rigid body mechanics is subdivided into statics, or the mechanics of objects at rest or moving at constant velocity, and dynamics, or the mechanics of objects in accelerated motion. Dynamics is further subdivided into kinematics and kinetics. Kinematics deals with the description of motion, whereas kinetics deals with the forces that cause or tend to cause changes in motion. One of the goals of research in biomechanics is to describe human movement and its causes in a quantitative manner. Doing so allows us to compare and track changes in performance. When conducting a movement analysis, some of the terms or measurements we might be interested in are speed, inertia, power, momentum, force, mass, weight, distance, velocity, and acceleration. One basic dimension we may want to measure is length. Length is used to describe the space in which movement occurs. When thinking about length, it is the most important dimension in sports such as shot putting or high jumping, where how far or how high is the actual measure of performance. Length is also an important dimension when we consider the anthropometry of athletes. An athlete's height may be one determinant of success in sports such as basketball or high jumping. As scientists, we should be using the International System of Units, or SI units, for measuring length. Thus, the SI unit of measurement for length is the meter. Time is another basic dimension we may have used to describe aspects of performance in sport. This may be how fast one can run a 100-meter race or how quickly one can react. Time can be measured in seconds, minutes, hours, days, weeks, months, years, and so on. However, all of these units are based on the second, which is the SI unit of measurement for time. Knowing the size of an object or an individual is another important measurement in mechanics, as this gives an indication as to the difficulty in starting or stopping motion. In mechanics, we refer to the property of an object to resist changes in its motion as inertia. Essentially, a larger object has more inertia than a smaller one. Keep in mind, weight is not the measure of inertia, rather mass is the measure of inertia. Weight is the measure of the force of gravity acting on an object. For example, on the moon, an Olympic shot putter would weigh less than he does on Earth, where there's no gravity in the moon. But he would still be just as difficult to start or stop moving horizontally, so his mass is unchanged. The kilogram is the SI unit for measurement for mass. And we will continue our discussion with Chapter 0. Thank you for listening.